Congratulations on finishing the power stage. The converter regulates, efficiency looks decent, and thermal performance is under control. And then, the input current waveform shows up on your screen and ruins your day. Instead of a nice sinusoid, you see narrow current spikes clustered around the peaks of the mains voltage. Your RMS current is worse than you expected. Harmonics are high, EMI gets touchy, and then suddenly, the front end of the supply isn't just a bridge rectifier and a bulk cap anymore, it's a design problem. If you have ever looked at an offline power supply and thought, why is the input stage causing this much trouble? Then you need to listen up, because power factor correction, or PFC, really sounds like a narrow topic, but in reality, it touches efficiency, compliance, thermal stress, magnetics, control loops, and EMI. And if you get it wrong, the rest of the supply pays for it. So today we're going to walk through what power factor actually means, why a simple rectifier capacitor front end creates ugly current draw, why boost PFC became the workhorse solution, where engineers run into trade-offs between CCM, CRM, and interleaving, and how practical details like line filters, PFC inductors, and simulation tools help you get a design across the finish line. You're listening to Wurth Elektronik's What's Up podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists, shining a light on topics like power conversion, EMI mitigation, magnetic components, and today, power factor correction. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast. We're going to start with one concept that makes the rest of this episode actually make sense, and that is power factor is not just a checkbox for compliance. It is a measure of how effectively your system converts input current into real useful power. In the ideal case, your input current follows the input voltage. Same shape, same frequency, in phase, and when that happens, apparent power and real power are close together, and your power factor is the near one. But in real power supplies, especially the basic offline front ends, you do not get that behavior. A bridge rectifier feeding a large bulk capacitor only draws current when the line voltage is high enough to recharge that capacitor. So current doesn't flow smoothly through the whole sine wave. It comes in short, high amplitude pulses near the voltage peaks. And that's the first big reframe. The problem isn't that the converter takes too much energy, it's how it takes that energy. Those narrow pulses drive up RMS current. They increase conduction losses, they stress components, and inject harmonic content back into the line. And that matters for a few reasons. One, utilities and standards bodies do not love harmonic pollution. Two, your own system, it doesn't love it either, because peaky current creates tougher thermal and EMI conditions. And three, once those power levels rise, that ugly front end starts showing up everywhere else in the design. You'll often hear two related ideas here. It's displacement and distortion. Now, displacement power factor is the phase shift piece. Distortion power factor is the waveform shape piece. In many rectifier front ends with a bulk capacitor, the current isn't badly phase shifted, it's badly distorted. Even if the current pulse is centered roughly where you'd expect, the overall power factor still drops because the waveform is nowhere near sinusoidal. That's important because it means that a supply can have a poor power factor even when voltage and current don't look wildly out of phase in the simple textbook sense. And now a few terms that do get tossed around a lot. It's THD. This is the total harmonic distortion. This is going to tell you how much of the current waveform lives in harmonics rather than the fundamental. Crest factor. This is the ratio of peak current to RMS current. High crest factor is your warning sign that current is arriving in hard spikes rather than a smooth, controlled shape. In a plain bridge plus capacitor input, both of those numbers head in the wrong direction. So the takeaway is simple. If your input stage takes energy in abrupt gulps, your power factor drops, harmonics rise, and the rest of the design gets harder. And that brings us to active PFC. The most common active PFC stage is a boost converter placed after the input rectifier. Its job is to shape the input current so that it tracks the rectified mains voltage while also regulating a higher DC bus. In other words, instead of letting the bulk capacitor decide when the current gets drawn, the converter decides, and it decides in a much more disciplined way. If you're on universal input, that boosted bus is typically around 380 to 400 volts DC. That higher, controlled bus then feeds the downstream stage, often an LLC or other isolated converter. So PFC is not just a compliance block, but it's the traffic cop between the line and the rest of the power supply. Now, here's the thing about boost PFC. It's popular because it solves several problems all at once. It improves power factor, it reduces input current harmonics, it creates a stable DC link for the next stage, and with the right control strategy, it does this efficiently over a broad input range. But not all boost PFC designs behave the same way. So let's talk about the conduction modes. In continuous conduction mode, or CCM, the inductor current never falls to zero within the switching cycle. CCM is attractive at higher power because peak currents are lower than in discontinuous modes, which helps with conduction losses and device stress. But the control is more involved. The current loop dynamics are more demanding, and diode reverse recovery losses can become painful depending on your semiconductor choice. In discontinuous conduction mode, DCM, the inductor current falls to zero before the next cycle begins. Control can be simpler in some cases, and turn-on behavior is easier, but peak currents are higher, which punishes your switch, your diode, and your magnetics. And then there's critical conduction mode, CRM, sometimes called boundary conduction mode, and that's the just right edge between CCM and DCM, where each cycle starts right as the inductor current returns to zero. A lot of practical PFC controllers use this because turning on at zero current eliminates diode reverse recovery stress, and it also simplifies current shaping. Now, the trade-off is variable switching frequency, and variable frequency can become a real EMC and filter design headache later on. And that's just one of the recurring themes in PFC. Every control mode solves one set of problems, but it also creates another. And now we get to the big one, because I know you're not just here to listen to my soothing voice. Let's go on to power level. At lower to mid power, a single-phase boost PFC is a very clean solution. But as power increases, the current in that one boost leg gets harder to manage. The magnetics grow, ripple current gets a lot uglier, and thermal concentration gets worse. And that's why interleaved PFC shows up so often in these higher power supplies. Instead of one boost phase doing all of the work, you run two or more phases shifted in time. And that spreads the current. It also reduces input ripple, it can shrink the passive components, and it helps with thermal distribution. You can think of it like several people carrying a load in a coordinated way instead of one person trying to lift the whole thing. Interleaving doesn't make the design magically easy. You still have current sharing, layout symmetry, control coordination, and EMI to worry about. But if it's done well, it gives you a more scalable front end. And then modern semiconductors push that conversation further. Silicon is still very much in the game, but wide-bandgap devices, these silicon carbide and the gallium nitride, these are going to open the door to faster switching, lower losses in the right operating window, and topologies that were once much less practical. And this includes bridgeless PFC and especially totem pole PFC. Now here's why. A traditional boost PFC pays a penalty in the input bridge because current always flows through bridge devices before it even reaches the boost stage. A bridgeless approach removes some of that conduction loss. A totem pole PFC takes the idea even further by replacing the diode bridge function with actively controlled switches. Now the catch here is that hard-switched totem pole was never practical with silicone MOSFETs because their body diode reverse recovery is brutal at these voltages. GaN and SiC devices largely eliminate that problem, which is exactly why totem pole went from academic curiosity to mainstream just within the last few years. The efficiency upside can be excellent, especially at higher power density targets. But the control, sensing, dead time management, and the EMI behavior, these are all becoming less forgiving. So this is not the topology that you choose if you want a relaxing week. And that's where good component selection matters. The PFC inductor is not just a value on a schematic. It's one of the core personalities of the stage. Its inductance, saturation behavior, copper and core losses, winding capacitance, and thermal performance, they are all showing up directly in the converter's efficiency and waveform quality. Wurth Elektronik's WE PFC family is built specifically for active power factor correction with an emphasis on high efficiency, good EMC behavior, and compact footprints. And there are different LT SPICE models available. We will include the links directly in the description of this podcast episode. But this means that you can compare real inductor behavior early in the design flow instead of discovering surprises on the bench. So that's a good example of how to think about PFC practically. You don't pick an inductor because the inductance number matches your spreadsheet. You're going to pick it because it behaves well in the actual converting that you're building. And speaking of practical design, EMI is never waiting politely in the background. It's looming in the corner, and it's in the room from the start. A PFC stage intentionally shapes current, but it also switches hard. Now that means that differential mode noise, common mode noise, parasitic ringing, and coupling paths through heat sinks and straight capacitances all become part of the story. A line filter is not decorative. It's often the last barrier between your switching converter and the mains. Wurth Elektronik's application note ANP015 on single-phase line filter design frames it exactly that way. Switch mode power supplies generate conducted interference on the main side, and a common mode choke combined with an X and Y capacitor is what suppresses it. Again, the link to that application note will be available in the description of this podcast episode. So, two useful reminders here. First, common mode and differential mode noise are not the same problem. They don't get filtered the same way. And that's why choke gets supplemented with X caps across the line and Y caps to earth. Second, your filter doesn't live in isolation. The interaction between the PFC stage, the input rectifier, the line impedance, and the EMI filter, it can create resonances and unexpected behavior. Filter design is a system task, not a copy-paste task. So a few rules for when PFC designs are starting to get messy. First, if the input current looks beautiful in simulation but ugly on the bench, check your sensing, your parasitics, and current loop bandwidth before blaming the controller. Next, if your thermals look worse than expected, don't just stare at the MOSFET. Revisit the choke, the bridge or synchronous path, and the RMS current distribution. Also, if EMI moves around as load changes, that is a clue that your operating mode, switching frequency behavior, or your filter damping needs another look. And if holdup time requirements keep forcing a huge bulk capacitor, remember that inrush limiting, holdup, and bus regulation are all linked. A bigger capacitor helps one requirement, but makes startup stress harder. A good engineer asks the bus energy question early in the project. Now let's move beyond classic offline supplies because PFC is evolving. In energy storage systems and grid-connected converters, digital control is becoming more attractive. This is because operating conditions vary so widely. Recent work presented at APEC, which is the IEEE Applied Power Electronics Conference and Exhibition, showed that adaptive digital control for PFC in energy storage systems points directly at that trend. More dynamic operating states, tighter performance expectations, and controlled strategies that adapt in real time rather than holding one fixed compromise. That doesn't mean analog control is obsolete. In fact, far from it. But the old mental model of PFC as a solved static front end, it's getting outdated. In systems with bidirectional energy flow, aggressive efficiency targets, and grid interaction, PFC is increasingly part of a broader control and optimization problem. So that circles back to why these magnetics still matter so much. Control can shape current, but magnetics store and release the energy that makes that shaping possible. If your magnetic design is poor, your beautiful control algorithm will simply supervise losses more intelligently. All right, so let's recap. Power factor correction is about controlling how a power supply draws energy from the line, not just how much. A plain rectifier with a bulk capacitor creates narrow current pulses, high crest factor, and high harmonic content. Active boost PFC reshapes that current and creates a regulated DC bus, which helps both compliance and downstream conversion. CCM, DCM, and CRM each bring different trade-offs in peak current, switching behavior, control complexity, and EMI. Interleaving helps at higher power. Wide-bandgap devices make topologies like totem pole PFC practical, but greater efficiency usually comes with tighter design discipline. And finally, real PFC success is never just about the controller IC. It's the inductor, the filter, the layout, the current sensing, the thermal path, and it's the way the whole front end behaves as one system. To view datasheets or order samples, please visit our website at we-online.com. And if you're working on an active PFC stage, the WE-PFC product page includes component details and those LT Spice models. For EMI and main side compliance, our application note ANP015 on single-phase line filter design and the mains filter application guide are also both practical starting points, and of course, those links are available in our show notes. So if today's episode saved your input current waveform, or at least your afternoon, share it with a colleague who's still blaming the controller, and tune in next time to get more design tips. Until then, keep your power factor high and your crest factor low. You're listening to Wurth Electronics What's Up Radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on interesting topics like power conversion, EMI mitigation, magnetic components, and more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.